Okay, hi everyone. My name is Julian, and this is my presentation on tight bounds for deterministic high-dimensional grid exploration. This is joint work with Sebastian Brandt and Jara Witto. First, let me introduce the problem we're considering. So it has been called the ANDS problem, which stands for ANDS nearby treasure search. So the setting is we have M agents that search for a treasure that is hidden in some structure, and the structure we're considering is a n-dimensional grid. So the standard setting is the two-dimensional one, and our main objective will be to try and generalize these methods to higher dimensions. Now, what do we know about this grid? Well, we assume that it's oriented, or in other words, that agents have a sense of direction. For example, you could think of this as each agent having a compass that points north, south, east, and west. For the computational power of these agents, we assume that they're just controlled by finite state automata. There have been variants that studied where agents are controlled by Turing machines, but in our setting, we will limit this to just finite state automata. Initially, we assume that all agents start in the same cell, but we allow them to start in different states. Or in other words, we can also think as each agent being governed by a different finite state automata. And we only allow agents to communicate if they occupy the same cell. So what do we mean by communicate? Well, one way to think of this is as exchanging some message, or another one is they can just sense the other agent's state. So they have full knowledge of the other agent's state. Now, how do the agents move around this grid? They move in kind of cycles. So in every time step, let's say, they look what is in their current cell. So they sense states of all ants or other agents that occupy the same cell. Then they compute, meaning they apply the transition function that is given by their finite state automata. And then they change their state and move to a new cell. So they can either move north one step, south one step, west or east. So we do not allow them to move like diagonally or so on. And of course, they can also choose to stay in the same cell. So there are two variants of this model that we will consider. One version is a synchronous setting where all agents are active at all time steps. So in every time step, each agent performs this look, compute, move cycle, and there's a global clock governing these actions. There's also the semi-synchronous variant where there's still a global clock. So the operations are still performed atomically. However, not every agent is active in every time step. So an adversary can create a schedule when which agent is active. For example, in the picture on the right, it could be that first the blue agent is active for 10 steps, then the green one for 20, and then maybe all of them for 50 or whatever. And in the semi-synchronous setting, of course, we would like that whatever schedule the adversary picks, the agents always find the treasure. Now, what is our objective? In our work, consider the objective of minimizing the number of agents that are needed to find this treasure. And the kind of challenge is that the distance that this treasure is away from the origin can be much larger than the state space of these automata. So think of this kind of distance to the treasure as an infinite quantity compared to the finite number of states. And let me also already mention that an equivalent formulation of finding this treasure is exploring the entire grid. And since this is an infinite grid, so eventually kind of visiting every cell. Good, so the kind of first thought I had when I saw this kind of model was that, okay, we have finite state automata. We would like to do this with a finite number of agents. Everything kind of seems finite. So how can we find something that is infinitely far away? Now, the answer to that is there is one kind of quantity that's not finite, and that is the distance between agents. So if you kind of look at the state of the combined state of all agents, one thing we have to take in account is their relative position. And in that regard, the distance between two agents can very well become kind of infinite or much larger than their state space. And one way to think of this is as a kind of measure of progress, or we can actually, or we will see that we can much more explicitly use this distance to encode certain information and use this to guide our exploration. Now let me quickly mention some previous work on this and related topics. So in the kind of context of exploring things, so there has been work on things like graph exploration, so general graphs. Some of you might have heard of the cow path problem, which is basically exploring a line. However, there it's done by a Turing machine. There has been work on exploring labyrinths, which are grids where certain cells are blocked. And finally, related to our work, there has also been work on trying to explore oriented grids. So kind of the first paper that introduced this ANS problem was by Feinerman, Corman, Lotker, and Sereni. And what they considered is trying to solve this problem with non-communicating Turing machines. So the problem or the question they were interested in is, can we achieve some sort of speed up over the kind of using multiple non-communicating agents compared to using just one? And they answered this in the affirmative. So they showed that if you have k non-communicating Turing machines, then they can explore or find a treasure at distance d in d squared divided by k plus d steps. This then was kind of studied from a different viewpoint by Emek, Langner, Witto, and Wattenhofer, where they considered the problem with using finite automata that can communicate. So here, the question is less about kind of how can we make them act independently, but much more how can they collaborate, since they are only finite state automata. And they showed that if they are allowed to communicate, if they occupy the same cell, the same kind of bounds as using Turing machines can be achieved. Now, another angle of approaching this problem, and the angle we're considering, is how many agents are needed. So we do not care about how fast we find this treasure, but just the minimum number such that we can guarantee that we'll eventually find the treasure. Now, for example, this was first studied by Emek, Langner, Stolz, Witto, and Wattenhofer, who showed that in a synchronous setting, this cannot be done by two agents. So one kind of easy example to consider is having a line where if you have just one finite state automata, it should be easy to see that this cannot explore the entire line, right? It can just kind of wander off in one direction. In 2 dimensions, if you have two agents, a similar kind of phenomenon can occur. However, they showed that using just 3 agents, it is actually already enough to explore the 2-dimensional grid. And if you have a semi-synchronous model, so there is, as I mentioned, not all agents are active at every step, they showed that you can do it with 4 agents, leaving open this gap. So this was then closed by Brandt, Witto, and Wattenhofer, who showed that in a much more involved proof than the lower bound of 2, that using 3 semi-synchronous agents is not sufficient to explore a 2-dimensional grid. Now, as I said, the problem we are interested in is how does this picture look like in higher dimensions? So Cohen et al. Actually conjectured that exploring the n-dimensional grid with some mean finite hitting time, so this is only relevant for randomized protocols, we will only consider deterministic agents, requires at least n+1 agents. So in the 2-dimensional case, this kind of makes sense, right? We have 3 agents, so for 4 it should be 5 and so on. However, this was disproven by Dobrev, Narayan, Pantry, and Pankratov recently, who showed that using randomness, Zn, the n-dimensional grid, can be explored using just 3 agents. And they also showed that using randomness, it can be without using randomness, so deterministically, it can be explored by 4 agents. So what is this kind of picture in the n-dimensional case? So for synchronous agents, they showed that 4 are sufficient and 5 semi-synchronous ones. So notice this kind of difference by 1. This is a standard kind of phenomenon. A lot of these synchronized protocols can be turned into semi-synchronous ones by adding 1 additional agent. And they showed that for the special case of d = 3, 4 semi-synchronous ones are enough. So what is our contribution? Well, we showed that in a semi-synchronous setting, 4 agents are enough, and in a synchronized, 3 agents are enough, kind of matching the bounds for 2 dimensions and completing the picture in the n-dimensional case. So let me repeat. In the n-dimensional oriented grid, can be explored by 3 synchronous finite automata, respectively 4 semi-synchronous ones. And we also get some extensions to a class of unoriented grids and a faster exploration using more agents, using similar techniques to Dobrev et al. Okay, so what is kind of the general exploration strategy? So think of each point as being represented by its coordinates. So here we have a point 1, 2, and we want to, well, somehow enumerate each coordinate. So in sometimes you just want to make sure that eventually every coordinate is visited. And the exploration now consists of going to the corresponding cell and going back to the origin, and then moving on to some other coordinate. Let me already kind of mention that if you know how to visit x, y, it is not so hard to visit -x, y, and so on, since this is just kind of inverting all operations in one direction, right? Okay, so one thing that Dobrev et al. Introduced was the notion of a stack. What does this mean? Well, this is basically just saying that we encode some information in the distance between 2 agents. Now, let us think, what kind of information do we need during this exploration? Now, we need kind of information on how to get to the current coordinate. Then once we are there, we need to have information about getting back to the origin, so being able to reverse this whole process. And finally, we need some way to change this stored information to make sure that we get to the next coordinates. Now, what kind of operations can we perform on this value of the distance? So we have 2 agents at distance s. Now, what kind of information can we gain about s? And how many agents do we need to gain this information? So the first thing is we can fairly easily learn s modulo x for some constant value of x. So think of x as being 2, for example. How can we do that? Well, let's say we have this black and blue guy at distance s, and the blue guy can just work towards black, and at every step increase a counter modulo 2, right? So as long as x is a finite value, this works perfectly fine. Now the problem is that once blue reaches black, and s is a very large value, so much larger than the state space, there's no way to recover s, right? So if we want to do that, we need a third agent, let's say the green guy, that keeps track of what was the value of s. So blue can first go to black, learn s modulo x, and then walk back to green to kind of recover the original configuration. Now, other kind of operations we can perform is we can multiply or divide x by some value. And how is this achieved? So here we actually start really relying on the fact that these operations are synchronous, or that all agents are active at every time step. So how do we multiply it by some number x? Well, if you think of x as being equal to 2, we want that after the operation, green and blue are located at distance 2s from the black guy. Now, how can we achieve this? Well, if agents were to move at different speeds, we could kind of do this, right? So if the green guy has to cover 3 times the distance of the blue guy, since blue just moves s, and green first moves s to the black guy, and then 2s until it should reach the blue guy, So if we just have green move at a speed of 1 step per iteration and blue guy only moves every 3rd step, we have this kind of proportional difference between their speeds. And this will ensure that they end up meeting at distance 2x. Now for general values of x, we can achieve the same. And we can, in a similar way, also divide by x, except that now the blue guy does not walk to the right, but it walks to the left, but with the same speeds. Good. However, again, as before, once you've kind of done these divisions or multiplications, well, if you do it once, right, you can just remember that you've done it and then restore it. But if you do it a bunch of times, this is not possible. So one way to do these operations and then remember the value of s is to again have an extra agent, now the yellow guy, to keep track of the value you previously had. Good. So this is actually already fairly close to what Dobrev et al. Do to achieve the exploration using 4 agents. The only missing piece is how to encode information in this stack. So Dobrev et al. Used the following kind of encoding. A coordinate pair xy is encoded as 2 to the x times 2 to the y plus 1. Now, why is this a good idea? Well, this allows us to read the coordinates as follows. We can check whether or not it's divisible by 2. So if x were equal to 0, this would not be true. So we would move on to the y coordinate. But as long as this is divisible by 2, we can kind of decrease x by 1 by dividing the stack size by 2, and then move 1 step in the x direction. And by move, I mean we move the entire stack structure. So all agents, the blue guy, the red, the green guy, the blue guy, the black guy, all move 1 step in the x direction. And then we carry on. We again check, so now s, the value of s is halved. So we again check if it's divisible by 2 and repeat. And once we know that it's not divisible by 2 anymore, well, we just need to move on to the next coordinate. And we can do that by decreasing the stack size by 1. So this is essentially getting rid of this number 1 here. Now, if we have some appropriate outer loop, this will kind of eventually explore the whole grid. Now let's consider an example. So at first, green checks divisibility by 2 by moving towards black, and then it moves back to blue. Now that, I mean, this value was 16, so it is divisible by 2. And now they actually perform this division, so green walks with speed 1, blue walks with speed 1 over 3, and they meet again at distance s over 2. And now they move the whole stack, in this case, in the y dimension, or by 1, meaning all agents move. Now, the problem and kind of the challenge that we aim to address is that we need to remember this original value, right? So once we've wandered off in this y direction, we do not know how many steps we need to take until we get back to the original starting point. So our solution to this problem was to choose a different kind of encoding. So we encode a coordinate xy as 3 to the x times 5 to the y. We were told that this is also called Gödel's encoding. More generally, we represent a number as the power of different primes. Now, why is this a good idea? Well, this allows us to perform a similar kind of idea. However, it allows us also to revert all these operations, even kind of an infinite number of them. So what do? Well, you can say that while this value is divisible by, for example, 3, we know that there's still some 3 factor in there, right? So we divide it by 3, but then multiply it by 2 to keep track of our kind of change. And then we move 1 step in this direction, and then again repeat this loop. If there are no more 3 factors left, we know that they were kind of all replaced by 2 factors. So we can just revert this whole process without any movement, and then move on to the next direction. Now, the nice thing about this is that we do not need this 4th agent to keep track, right? And this allows us to do the whole thing with just 3 agents. So to recap, We start with s equal 3. This is for technical reasons. And repeat that we choose some coordinate and some direction for each coordinate. Just go through all of them, right? This is a finite number. And then we walk to the coordinates described by s, as I said, with the previous mentioned encoding. And then we go back to the origin. And finally, we increase the value of s by 2. Now, some final remarks. Well, everything that I talked about can be adapted to the semi-synchronous model using an extra agent. So whenever we relied on synchrony, we can achieve a similar thing by having one agent push the other agents around. So it will go to one guy and say, okay, you're now allowed to move 1 step. And it will go to the other guy and say, okay, you're now allowed to move 3 steps, and so on, and just move in between those agents. And this allows us to turn kind of a large number of synchronous protocols into semi-synchronous protocols. Now, this stack actually is not super reliant on the grid being oriented. We can achieve something similar if we assume that there's kind of at least one direction where walking in it repeatedly leads us to infinity. Let me mention one thing that's kind of neat is that there's some handrailing technique. So even if you have an unoriented grid and double the number of agents, basically everything works as it did previously. And we show that being a bit more careful, actually this special class of unoriented grids can be explored using the same number of agents. And finally, using techniques of Dobrev et al. And a different kind of exploration strategy, but still the same encoding, we show that we can show that the exploration time can be sped up. So think of this as kind of being polynomial versus exponential time. Good. So some open problems. One of them is is it possible to prove better lower bounds for general grids? Getting polynomial time with the same number of agents as we did for exponential time. Improving the semi-synchronous model using randomness. So in this case, actually the bound is, there's this kind of the only setting in the n-dimensional case where the bound is not tight. And finally, is it possible to reduce computational power of agents? So instead of having finite state automata, can we replace them with, for example, a movable marker? But this is it. Thanks for your attention. If anything was unclear, please check out the paper. And again, thanks.